left off, you had a cliffhanger, and that cliffhanger happened to be they were thinking about factoring out Fn from two different equations. You know the values for almost everything in here at this point, and now it's just kind of the algebra, like what is it that you do to actually get a numeric answer to this. So there's a number of things that you can do. What I would recommend is that since you see Fn in both of these equations, here in equation number 2, here in equation number 1, what you can do is you could sort of solve both equations for Fn. So in the first equation, for example, you can kind of work this down to where you have it in the form mg over mu s sine theta plus cos theta equals Fn, and then plug that value into here for Fn and solve. So when I did that with this equation, I got that Fn is equal to 10 times the mass of the car. So putting that in on this side of the equation over here gives me 10 times m. It's not 10 meters, it's 10 times m multiplied by sine theta minus mu s cos theta. And then, of course, now the mass cancels out from both sides. It might not be obvious that that is what happens, but we don't need it to solve the problem. And putting in all the values that you have for v, I'm sorry, not for v, for r, and for theta, and for mu, because mu s is told to you in the problem to be 0.3. I find that v, and this is the minimum speed, by the way, is equal to 16.4 meters per second. So my challenge to you now is to find the maximum speed that the car could go on the hill and not drift up the hill, okay, in this direction. If the car tends to drift up the hill, what is going to happen is that you'll have a friction vector that points down the hill, here highly exaggerated. So you get the idea that you'll have to resolve it and have a friction component this way and a friction component this way. So you'll need to repeat the kind of operations that we did in the first video, where you're thinking about all the stuff that I kind of wrote down in this area on the first video in terms of resolving the friction vector. Also, notice what happens in the direction of vertical here, that you end up thinking about summing the weight vector and the y component. What you should find is that V max is about 32 meters per second if you do this all correctly. And so in the end, for this problem, we find that the velocity must be greater than 16.4 and less than 32 meters per second in order for the car to stay safely on a banked curve of 36 degrees with a radius of 78 meters.